In the last video, we showed that for a given energy level E, we are able to construct this constant K, which can take on two possible values, either plus or minus the square root of 2me divided by h bar. And then taking this value of K, we can substitute it inside this expression, and it would give us a function xi, x, and t that satisfies the Schrodinger equation. So it seems like all we have to do now is to normalize this expression. But then we can actually show that it is actually impossible to normalize this, because when you take this integral over here, when you take the absolute value square of the wave function, we will have to take the conjugate of this e term and then multiply it with itself, so it just cancels itself out. And all you're going to have left is the absolute value square of the constant a. And then you're going to integrate this from negative to positive infinity. So this is just equal to infinity. So this expression is actually not impossible for us to normalize. So this is actually not a physically realizable state. So for a particle inside this potential, it is impossible for the particle to have such a wave function because it is not normalizable. So it seems like in spite of all our efforts, we have failed after all. But then we can actually still use this expression over here to construct a wave function that is normalizable and that will satisfy the Schrodinger equation. And then we do that by considering this expression over here. So we have a 1 over square root of 2 pi. So I'm just going to write this out first. And then we have a phi of k. This is a function in terms of k. And then we have this expression 2mt and then dk. So this expression over here, this is normalizable and this satisfies the Schrodinger equation. So for a particle inside this potential, this is how you can represent the wave function of that particle. So this 1 over square root of 2 pi over here, this is just a technicality that arises from Fourier transform. You will be able to understand where this comes from when you attempt problem 2.20. So I highly recommend you do this problem as soon as possible. So doing this problem, you'll be able to understand the mathematics involved in constructing this solution. So this is just a technicality that arises from Fourier transform. Now this is a function in terms of k, this phi of k over here, and this is going to be determined by the initial wave function, so xi x is 0. So later on I'll tell you about a formula that will allow you to obtain phi of k where if you're given a initial wave function. And then this expression over here, you can see that it is just this expression over here. So here you can see that we're integrating this expression with respect to k. So what we're doing is basically we're taking this expression and then we're taking a linear combination of a whole bunch of different possibilities. So you can see that k will range from negative to positive infinity. So we're adding up a whole bunch of different possibilities for xi xt's, and each one of them will correspond to a different value of k. And then you can actually draw a parallel between this case, this is for the free particle, with one of the cases we saw earlier. So if you take a look at the expression for the wave function for the infinite square well, remember that for the infinite square well, the general solution for the wave function is given by this expression over here. And then for that, for the infinite square well, the energy level was given by this formula. So you can see that for the infinite square well, in order to construct the wave function, we take a linear combination of a whole bunch of different smaller wave functions, and then each one of those would correspond to a certain energy level. And then for the infinite square well, we had a discrete spectrum of possible energy levels. And then you can see that we're pretty much doing the same thing for the free particle, only this time we don't have any restrictions on the energy levels. So instead of a discrete spectrum, we have a continuous spectrum, and you can see that for the k over here, it ranges in a continuous spectrum from negative to positive infinity. And so you can kind of draw a parallel between the two cases, which could help you better understand what's going on in this expression. So they're pretty much doing the same thing. All we're doing is taking a linear combination of kind of like smaller expressions, and then each one would correspond to a different energy level. For the infinite square well, it would correspond to different energy levels within a discrete spectrum, and then for the free particle, it would be decays would correspond to a continuous energy spectrum. So if you're wondering about the phi of k, we can actually find phi of k using this formula over here. So once again, you can prove this formula and you will understand more about it when you do problem 2.20. So I highly recommend you do this problem. And from that problem, you can easily see that you can actually construct your phi of k by using this expression over here. So given an initial wave function, we can take this integral, and then this would give us this function phi of k, and then we can take this phi of k and then substitute it inside in this location over here, and this final expression that we have will be a wave function that is normalizable, that satisfies this initial wave function, and that will satisfy the Schrodinger equation. And so that is how you construct a solution for the free particle. So for the next video, I'm going to move on to the example to see, to show you all how all these concepts and all these formulas will work out in a specific setting. And once again, I highly recommend you do problem 2.20 because it would shed a lot more light on the mathematics involved in this solution over here. And I've actually already uploaded a solution video to this problem, so check that out if you're interested. And we will move on to the example in the next video.